Welcome to M8307 Numerical Analysis course. In this lecture, we will continue our discussion on matrices. First, we will give a definition. It is determinant. The determinant is a function assuming a square matrix as an input and returning a scalar number. So, it is a spatial function on the set of square matrices of any dimension, and it will return just a number, real number. It is denoted by between two vertical bars. The matrix A is also like absolute value, okay, or determinant A, that A. In particular, if the dimension is 1, if we have one dimension square matrix, then the determinant will be the number itself, so the entry itself, A11. Okay, so if we have two-dimensional matrix, then our determinant will be A11 times A22 minus A12 times A21. So to see it better, we draw a diagonal line from left to right and from right to left, and then we say the product on this diagonal will be positive, and the product on that diagonal will be negative. So this will be basically A11 times A22 minus A12 times A21, which is here. Okay, so if we have three-dimensional matrix, three-dimensional square matrix, in this particular case, our determinant is this one. Okay, so we compute determinant like that. So to see this better and memorize better, we basically add these first two row below the matrix itself, okay, and then this is identical to the first two rows. It's a copy, okay, and then we start again drawing diagonal lines like this one. First one will be this, and the second will be this one, and the last one will be this. And then we say these are all positive from left to right. These are all positive. And then we take the product A11, A22, A33 and say this is positive. And then A21, A32, A13, so which is here, is also positive. And then A31, A12, A23, which is here, also positive. Okay, once we are done with the diagonal from left to right, we do the same from right to left. Okay, so we draw the diagonal again, but this time we say these are negative. So this will be A13, A22, A31 with a minus in front, and then we will continue like that. So this will be, the last one will be A33, A2, A12, and A21, so which is here. Okay, so we find the determinant like that for three-dimensional matrices. Okay, in particular, if we have larger matrices like 4 by 4 matrix, or any matrix bigger than 4 by 4, okay, then we have to drop back down to the smaller matrices, 2 by 2 or 3 by 3 matrices, to take the determinants by using minors and cofactors. Okay, so minors and cofactors will be introduced next. First, the minor Mij is the determinant of a square matrix formed by deleting the ith row and jth column from the square matrix A. So we have Mij, it means delete the row I and column J, and then take the determinant of the remaining matrix. Also, the cofactor will be similar to the minor, but this time we have either positive or negative sign. So if I plus j is an even number, then we have positive minor itself, or if we have a plus j is an odd number, then it will be the minus minor itself. Okay, so cofactor will be this. Okay, so in this example, given a matrix A, M12 will be the determinant of this submatrix, How can we find this submatrix? This is basically found by deleting the first row, and we have 2 here, second column. So this will be 2032. 2032. So when we take the determinant of this matrix, this will be basically 4 times 4 minus 0, which is 4. Okay, so M31, the minor corresponding to the entry 31, A31, will be found by taking determinant of this and that, determinant of this submatrix. So 3, negative 1, 1, 0. So we need to delete the third row and first column, and then the submatrix we obtain will be the matrix we care about, and then we take the determinant of this submatrix, and it will give us the minor. So here we have 3 times 0, which is 0, 1 times negative 1, which is negative 1, but we need to take the negative for this diagonal, so this will be a positive one. Also, the cofactors can be found like multiplying the minor by negative 1 to the power I plus j. In this particular case, I plus j will be 3, so this will be an odd number. So 4 will be negative 4 for the cofactor 2, 1. Okay, so for cofactor 3, 1, if we add 3 plus 1, we will obtain 4. So this is an even power, so this will be just 1. So minor itself will be the cofactor, so minor is 1, so cofactor will be. In general, picking a row, say this is the ith row, and using cofactor corresponding to its entries meaning the entries on that row, determinant can be found by this formula. So determinant A will be equal to, say we fix the row number I. Okay, so the first entry on that row times its cofactor plus the second entry on that row times the cofactor plus following the same pattern, we will have the last entry on that row times the cofactor of that of this entry. If we add all of this, we will obtain the determinant. Similarly, we can do the same with a column. So say we pick a column number j, okay, jth column, and then we can still use similar formula. This time we will have the cofactors times the entry on that column. Okay, so this summation will give us the determinant. Okay, no matter which direction you go, either you can choose a row or a column, you can still obtain the same determinant for it. Okay, so both of these formulas give the same determinant regardless of the choice of which row or a column you choose. Therefore, picking a row or a column, picking the row or a column having lots of zeros reduces the number of computations. Okay, so if we have lots of zeros on a row, this aij's will be 0 mostly, and then this addition will simplify, because if this is 0, we don't have to find the cofactor itself. So an example, we have this matrix and we want to find the determinant of this matrix. Okay, so if we pick this row, sorry, this column, then we will have 2 zeros already. So when we take the determinant, we don't have to worry about finding cofactors corresponding to these entries. Okay, so the determinant will be the A13 entry times the cofactor C13 plus A23 times C23 plus A33 times C33. But we know these two entries are 0, so these two terms will cancel out. This and that will cancel out, and we will end up with only one entry times its cofactor being the determinant. Okay, so this entry is basically -1, and the cofactor corresponding this entry will be, if we delete this column and this row, sorry, this row and this column, we will have 2, 1, 3, 1, 2, 1, 3, 1. If we take the determinant, this will be negative 1. Negative 1 times positive 1 minus, sorry, negative 1. This will be just 1. And we can find the determinant of this matrix easily like that. Okay, so you should try to get the same answer by picking another row or column. So for example, you can pick, say, this row or that row, maybe this row, to make things harder. Okay, so you should, no matter which one you choose, you should get the same answer one. Okay, next we have a definition for we will start our discussion on system of linear equations. First, we will give a definition for linear equation for arbitrary constants a1, a2, an, and also some other constants c, and unknowns x1, x2, that's xn. These are the unknowns. The equality a1 times x1 plus a2 times x2 plus dots an times xn equals c is a linear equation. This is linear because we have the unknown times some constant only. If we had instead x1 squared, then this wouldn't be a linear equation, or x1 times x2 will not give us a linear equation. But if we have an equation in this form, some constant times the unknown plus some other constant times the other unknown, then this will be a linear equation. Okay, a solution of this linear equation is x1, x2 dots xn values that satisfies the linear equation at the same time. Okay, so this will be a set of numbers. So x1, say, is some number and x2 will be another number, and all of these numbers will satisfy the linear equation at the same time. Then we say this is a linear equation, this is the solution. Okay, so we have a linear equation here because we have some constant times x1 plus some other constant, which is 1 in this case, another constant times x2 plus some other constant times x3 is equal to some constant. So this is a linear equation with solution x1 equals -4, x2 equals 2, and x3 equals 0. If you substitute -4 here, this will be -8, and then plus 2 will be -6. 0 times that will be 0. -6 is equal to -6, so this will satisfy the equation, so this is the solution. Okay, and also if we substitute these numbers, -3 for x1, this will be -6 times -6 plus 0 plus another 0 will give us -6. -6 equals to -6, so this is also a solution. Okay, so this means we may have a linear equation may have more than one solution. Okay, so linear equation may have more than one solution. How can we illustrate all possible solutions of a linear equation? This is simply solving for this equation for x2. We obtain, if we leave x2 alone and move all the other terms to the right, we will have x2 is equal to -6 minus 2x1 minus √5 x3. Okay, here this means given x1 and x3, we can obtain x2. Okay, so this means if we choose x1 equals t, some arbitrary number t, and x3 equals s, then we can find x2 as -6 minus 2t minus √5s. Okay, so this is our solution for our linear equation. If we substitute, for example, -4 for t and 0 for s, we can find x2 equals 2, and this will be the first solution above. We have given this first solution here, -4, 2, and 0, -4, 2, and 0. This is a solution already, and we can recover this solution by using this notation. Okay, then one can also find any particular solution to the linear system following similar fashion. So if you for example, say t is 0 and s is 1, or t is 100 and s is basically 1 million. So this will be still a solution as long as we apply the same formula. Okay, so this will be a family of solutions. Next, we have another definition. A system of linear equation is a collection of more than one linear equation. Okay, we have given the definition for a linear equation, but here a system of linear equation will be the collection of more than one equations. It is like this one here. We have 1, 2 goes all the way up to m, so we have m equations. Okay, m equations solving at the same time. We are solving solving all of this at the same time, and this is more than one linear equation involving the same set of unknowns. So x1, x2, xn's are all the unknowns of of each linear equation. A linear system with n unknowns and m linear equations is given like in the rectangle here. Okay, so here we have aij's. These are the constant coefficients of unknowns, and bj's are the constants of linear equations. Okay, the coefficients of unknowns listed here, a11, amn, like all of these constants, coefficients are very similar to the entries of a matrix. This is not a coincidence, since we can rewrite this system as a matrix vector product. So this equation can be rewritten as a matrix vector product. How is this possible? So if we have this matrix, say, and the vector of unknowns, if we take the product of this matrix times this vector, we will obtain this values. And then taking this product, we will have, for example, this equation first, and then the next equation, and the last one. So if you check this with the equation itself, we see these are basically the same. Okay, so this means any linear system, any system of linear equations can be rewritten as a matrix vector product like ax equals b. Okay, here A is known as the coefficient matrix, X is the vector of unknowns, and B is the vector of constants. Rewriting a linear system as a matrix vector product Ax equals B allows us to employ matrix algebra to simplify finding out solutions. Okay, so this will simplify our process. Given Ax equals B and letting A be an invertible matrix, this is an assumption, say this is an invertible matrix, we multiply the equation by A inverse from the left to get this. A inverse times Ax equals A inverse times B. Here we have identity times X. Identity times X is equal to X itself, so X will be equal to basically A inverse times B. Okay, so for any given linear system Ax equals B, if we can somehow find the A inverse, the matrix A inverse, we can easily obtain the solution. Okay, so the process of finding a solution to the system Ax equals B is reduced to a matrix vector product once we compute A inverse. Okay, but finding A inverse is not a simple job. We will continue our discussion on finding this A inverse, or solving system of linear equations on the following lectures. An example, consider the following linear system. So we have a linear system here. This is a simple enough linear system, two equations with two unknowns. Okay, we can rewrite this equation as a matrix vector product, like the coefficient matrix times unknowns is equal to the constants. Okay, so the coefficients are 1, 2, 3, 5. 1, 2, 3, 5 will be the coefficient matrix. If you multiply this out, you will obtain the same equation, the original equation. Okay, say somehow we can find the inverse of this matrix. Okay, say the inverse of this matrix is given like that. If you multiply this both equations from the left by this matrix, then we will have basically this equation, and then here we will have identity. If you multiply them out, you will see you will obtain identity, and identity times the vector of unknowns will give us the vector of unknowns itself, and here the matrix vector product will give us this vector, and this will be basically equal to our solution. So x1 will be -1 and x2 equals 1. So if you substitute -1 here and 1 there, you will see -1 plus 2 will be 1, and then -1 here and 1 there, so -3 plus 5 will be equal to 2. So this is really a solution. So that's all for this lecture. Thanks for watching.